Hello, everyone. This is Rugambwa Gloria. I'm a member of Group 17, Machine Learning. And this video basically is to talk about and explain the two models I used to train my data set. But before I go further into that, I would like to first give a brief introduction of our project. And also, I would like to apologize for my video, which is not showing at the moment. Yeah. So the project that we are handling is the design and implementation of a smart food supply chain management system for restaurants in and around Makerere University. So why we chose this project is because we made a research and found out that there's a big problem being faced by the cafeterias and the kiosks and the vendors within Makerere University. There is a huge demand and supply mismatch. And also there is also overproduction of meals leading to food wastage, occasional stockouts during peak demand, poor inventory coordination. So let's give an example of Kosis Cafeteria. It supplies, let's say, a given food item, such as pancakes, and in a certain academic period, for example, the exam period, there is a low demand, there is a low sales of the pancakes. This is because during exam period, people are in and out of the university, or basically they come in to sit papers and leave, which is different from the normal teaching period where students spend the entire day, or let's say per se half a day within the campus. So the demands during the teaching period are different from the levels of demand during the exam period. So what this project is about is it's going to give a display. It's going to make a calculation, provide cafeteria owners, provide the kiosk vendors with data, with statistical data on how to plan for their items. Yeah. So that they can reduce on the food wastage, and also to also know how much proper planning, and also help them generate profit, high levels of profit. So with that said, let me now rush to the models we used. First and foremost, the first model I applied into this project was the Bayesian network model. So what is this Bayesian network model about? It is a machine learning model that uses probability to understand how different things in the real world are related to each other. So you're going to think of it as a map of a cause of an effect. It's going to show you which factors affect the other factor and by how much. So in relation to our model, the Bayesian network is going to show the manager what affects the demand. Yeah? What affects the revenue generated. So to begin with, it has two parts. It has the structure, which we have down here. This structure is, as you can see, it's involves arrows, 9 edges, and each of these arrow means that the variable at the start of the arrow has a direct influence on the variable at the end of the arrow. So in this diagram, as you can see, is weakened from the analysis, from the computation. This was the structure we're able to obtain, and it shows that is weakened. What does that mean? A day within the weekend period affects the waste level and has an influence on the demand. Yeah. So that means it can either be, it being a weekend can cause high wastage level. It being a weekend can reduce demand, because we realize that during the weekend, few people are within the campus, because many people during weekend days, Saturday, Sunday, most of their people either go out or go home. Yeah, so the demand is different from during the weekdays. So as I said earlier on, the two parts is the structure. Then we have the parameters, which are the actual probabilities that say how much one variable affects the other. And these parameters are stored in conditional probability tables. So our conditional probability table is here. As you can see here, these are the computations the model were able to use for our model. Then next we have the parameters and the hyperparameters. So what exactly are the parameters in this case? So for the parameters, they are the probability values inside the conditional probability tables. So in this case, as you can see, we have is weekend. Then the probability was obtained through two values, which is the weekend and the weekday, times one combination, which is equals to 2. So this table shows us our land parameters, yeah? Then the hyperparameters, they are the design decisions you make before training. These ones are not got from the data, but instead they are the things that we choose as the data scientists. They're the ones we are going to use in order to tune or to improve the model performance. So from using the Bayesian model, the hyperparameters were able to come up with the number of the variables, and were able to reduce from the 30 original columns within our data set and obtained 8 meaningful ones. We had the number of the bins, which is continuous values such as revenue, waste, portions. These were split into 3 categories, which is low, medium, high. Yeah. Then we had the Laplace smoothing alpha equivalent to 1.0. This one controls how much smooth out a zero count combination. Then a higher alpha makes all probabilities more uniform. Then the lower alpha keeps the probabilities closer to row counts. Then we have the network structure, as I had said, the structure, the DAG with the 9 edges. Then the sample size is our entire data set. So basically, that's our Bayesian network. Now let me take you through how does it work. It basically uses the probabilistic values that we got from the CPT table. Yeah, and also we use the inference method whereby we generate query questions, that the model will then predict the answer using that DAG structure. So the next model that I used and implied was the SARIMA model. So first of all, SARIMA stands for Seasonal Autoregressive Integrated Moving Average. So to begin with, SARIMA, it is a model that is an extension of the ARIMA model, and it explicitly models seasonal patterns in time series data. So it is one of those mostly used classical statistical methods for time series forecasting. And in this case, we really need it because the demand and supply is based on the time series. In terms of weekdays, in terms of academic period. Yeah. So our model architecture is here. That's our model architecture. And we're able to see that there's the Makerere kiosk, which is our data set, goes through pre-processing the input data, down creates clusters, 3 clusters, trains and splits the data. Then it goes through the SARIMA model core where we have the SARIMA 9, the 6 variables. Then when it's done being trained, it now moves out as an output. Yeah. So basically, this SARIMA model has a compact annotation that it follows, P, D, Q, P. Each of these letter cases has what it stands for, where the lowercase is a non-seasonal component, and then the uppercase is a seasonal component. Then the S stands for seasonal period, and in our case, the S stands for 7 days a week, because we are dealing with demand and supply within the 7 days of a week. So according to our data set, we're able to interpret the variables as shown below. This is our component, our variable table. S represents 7, the weekly seasonality. D can either be 0 or 1, and it's computed using the ADF stationarity test. Then capital D, which is a 1, which is 1 seasonal differencing to remove weekly trend. Then we have the small p and q. Then the capital, these are the letters in the notation, the expression, the SARIMA expression. Yeah. So it runs through a statistical optimization process that involves data preprocessing, parameter estimation, and diagnostic checking. So what does that mean? The data preprocessing, as we had seen in our picture, there is passing of the dates, PCA dimensionality, creating the three clusters, ADF stationarity test. Then after that data preprocessing, we are able to see it goes through parameter estimation and diagnostic checking. So this is the structure. Parameter checking is within the SARIMA model core. Then output, that's where the diagnostic checks takes place. So about this model, it basically has parameter estimation via MLE, which is maximum likelihood estimation. And the goal is to find parameter values that maximize the probability of observing the data that was actually seen.